Welcome! In this session, we'll explore LeetCode problem number 505, the maze 2. This problem challenges us to navigate through a maze and find the shortest path from a starting point to a destination. Get ready to dive into an exciting pathfinding problem and uncover efficient strategies for solving it. In this problem, we have a maze represented as a 2D grid, and a ball that can move in 4 cardinal directions: up, down, left, or right. However, the ball doesn't stop immediately when it changes direction. Instead, it keeps rolling until it hits a wall or the boundary of the maze. Once the ball stops, it can choose a new direction to roll. Our goal is to determine the shortest distance the ball must travel to reach a given destination position in the maze. The distance is defined as the total number of empty cells the ball passes through, excluding the starting cell but including the destination cell. If it's not possible for the ball to reach the destination, we return -1. The input consists of the maze itself, the starting position of the ball, and the destination position, all provided as coordinates in the grid. The maze cells are represented by 0 for empty spaces and 1 for walls, and the grid size can range from 1 by 1 to 100 by 100. To understand the problem better, let's look at an example. Here, we have a 5 by 5 maze, where empty cells are marked with 0 and walls are marked with 1. The starting position of the ball is at the top right corner, 0, 4, and the destination is at the bottom right corner, 4, 4. The ball can roll downward directly to the destination, passing through the empty cells, 1, 4, 2, 4, 3, 4, and finally reaching 4, 4. The total number of cells passed through, which is our distance, is 12. The total distance for this path is 12. Now, consider a second example with the same maze and starting position, 0, 4, but a different destination, 3, 2. In this case, the ball cannot reach the destination because the path is blocked by walls. Since no valid path exists, the output for this example is -1. Here's another example with a different maze. The ball starts at 4, 3, and needs to reach the destination, 0, 1. To do this, the ball first rolls left to 4, 0, then rolls upward to 0, 0, and finally rolls right to 0, 1. The total distance traveled in this case is 7. This demonstrates how the ball can take multiple directional rolls to reach its goal, and the shortest valid path is what we are calculating. Finally, the problem comes with a few constraints. The dimensions of the maze, m and n, must be between 1 and 100. Each cell in the maze is either empty, represented by 0, or a wall, represented by 1. The starting and destination positions are both guaranteed to be empty spaces, and their coordinates are within the bounds of the maze. Additionally, the maze will always contain at least 2 empty spaces, ensuring that there is room for the ball to move. With these constraints in mind, we now have a clear understanding of the problem requirements and can start thinking about how to solve it efficiently. To tackle LeetCode problem number 505, the maze 2, our goal is to determine the shortest distance for a ball to travel from a starting position to a destination within a maze. The ball has a unique movement behavior. It continues rolling in a straight line until it hits a wall. This makes the problem distinct from typical pathfinding questions, as we must account for how far the ball rolls before changing direction. One approach we might consider is using depth-first search, or DFS. This method explores all possible paths recursively, allowing the ball to roll in each direction until it encounters a wall. By marking visited positions, we can avoid revisiting the same points and creating cycles. However, while DFS is intuitive for pathfinding, it is not well suited for finding the shortest path since it doesn't prioritize minimal distances, it simply explores deeply before backtracking. As a result, DFS can lead to inefficient exhaustive exploration. The time complexity of this approach is O(m*n* max, m(n), where m and n are the maze dimensions, and the space complexity is O(m*n) to keep track of visited positions. While useful for finding any path, DFS falls short when the shortest path is required. A more optimal approach is to use Dijkstra's algorithm, which is specifically designed to find the shortest path in a weighted graph. In this problem, the maze can be treated as a graph where the nodes represent positions, and the edges correspond to the distances the ball rolls in each direction. Using a priority queue, we process positions in order of their increasing distance from the start. This ensures that once we reach the destination, we've already found the shortest path. One key observation here is that the ball's rolling distance can be treated as the weight of an edge, which aligns perfectly with Dijkstra's greedy strategy. The algorithm's time complexity is O, m*n*, log, m*n, driven by the priority queue operations, and its space complexity is O, m*n, due to the storage required for the queue in visited positions. Although Dijkstra's algorithm involves a slightly more complex implementation due to the priority queue, it guarantees the shortest path efficiently. Another option we might consider is breadth-first search, or BFS. Like Dijkstra's, BFS explores all positions level by level to ensure the shortest path. However, BFS requires additional bookkeeping to handle the ball's rolling mechanics, where distances need to be recalculated for each direction. This makes BFS less straightforward than its typical application in unweighted graphs. While BFS can ensure the shortest path, it is less efficient than Dijkstra's algorithm due to redundant distance calculations. In terms of complexity, BFS has a time complexity similar to Dijkstra's at O, m*n*, max, m*n, and a space complexity of O, m*n. However, the need to compute rolling distances for each movement direction adds extra overhead, making it less appealing for this problem. After weighing the options, Dijkstra's algorithm emerges as the most fitting and efficient solution. The ball's unique rolling behavior naturally translates into a weighted graph scenario, where the distances traveled serve as edge weights. By leveraging a priority queue, we ensure that positions are explored in order of increasing distance, minimizing redundant calculations. This guarantees that the shortest path is found with maximum efficiency. One key insight that solidified this choice was recognizing that the rolling distance could be modeled as an edge weight. This alignment with the classical shortest path problem made Dijkstra's algorithm the ideal choice. Its greedy nature, combined with the efficiency of the priority queue, provides an optimal balance between correctness and performance. When comparing the three strategies, DFS, BFS, and Dijkstra's, the trade-offs become clear. DFS can find a valid path but is inefficient for the shortest path due to its exhaustive search. BFS guarantees the shortest path but involves redundant calculations when handling rolling distances. Dijkstra's algorithm, on the other hand, stands out as the most efficient approach for weighted graphs, guaranteeing correctness while scaling well with larger mazes. The final implementation involves initializing a priority queue to manage positions by their rolling distance, maintaining a visited set to avoid cycles, and iteratively processing the node with the shortest distance. For each position, we calculate the rolling distance in all possible directions, updating the queue and visited set as necessary. Once the destination is reached, the shortest distance is returned as the result. This systematic approach ensures that we achieve both correctness and efficiency, making Dijkstra's algorithm the optimal solution for this problem. To solve the problem of finding the shortest path in the maze 2, we need to account for the unique rolling behavior of the ball. Unlike typical grid problems where movement is step by step, here the ball continues rolling in a straight line until it hits a wall. This makes the shortest path calculation a bit more complex, and a priority queue combined with Dijkstra's algorithm becomes an ideal choice. First, we represent the maze as a 2D grid, where open spaces are marked as 0 and walls are marked as 1. Along with this, we are given the ball's starting position, the target destination, and the maze grid itself. Next, we initialize a priority queue, which will store tuples of the form, distance, x, y. The distance represents the total travel cost to reach a specific position. By pushing the starting position into the queue with a distance of 0, we ensure the shortest path is always processed first. To keep track of progress, we use a 2D array called distances, which is initialized to infinity for all cells. This array will store the shortest distance to reach each cell in the maze. For the starting position, we set the distance to 0. Additionally, we define the 4 possible directions the ball can roll: up, down, left, and right. These are represented as direction vectors to simplify the movement logic. Once the priority queue is ready, we begin processing it. This involves repeatedly popping the node with the smallest distance. If this node happens to be the destination, we can return the current distance as the shortest path. For every direction, the ball rolls continuously until it hits a wall or exits the maze boundary. While rolling, we count the steps taken and track the new position. The total distance to this new position is calculated by adding the steps to the current distance. If this new distance is shorter than the previously recorded distance for that cell, we update the distances array and push the new position into the priority queue. After updating the distance for the new position, we ensure that the corresponding node is pushed into the priority queue as new_dist, new_x, new_y. This guarantees that we continue processing paths in ascending order of distance. However, we must also handle edge cases. If the destination is unreachable, the priority queue will eventually become empty without finding a valid path. In such cases, we return -1 to indicate that the destination is unattainable. Additionally, we ensure that each cell is only reprocessed if a shorter path is discovered. Finally, the result is determined by checking the value in the distances array for the destination cell. If it remains at infinity, we return -1. Otherwise, the shortest distance to the destination is returned as the result. There are a few key insights that help us understand this solution better. First, the rolling behavior of the ball means that intermediate cells it passes through while rolling are not valid stopping points. This makes it crucial to simulate the rolling process accurately. Second, the use of Dijkstra's algorithm ensures that we always prioritize the shortest path at each step, which is essential for efficiently solving this type of problem. Lastly, maintaining the distances array prevents unnecessary reprocessing of cells, as each cell is only updated when a shorter path is found. Together, these insights enable us to solve the problem effectively and efficiently. The solution relies on three main data structures. First, the priority queue, implemented as a min heap, stores nodes in the form of distance, x, y, tuples. This ensures that the shortest path is always processed first, which is central to Dijkstra's algorithm. Second, the distances array is a 2D grid initialized to infinity, used to track the shortest known distance to each cell. This helps us avoid revisiting nodes unnecessarily. Third, the direction vectors simplify movement logic by representing the four possible rolling directions: up, down, left, and right. These data structures work together to ensure the solution is both correct and efficient. Several key operations are involved in implementing this algorithm. First, rolling the ball in a given direction involves continuously moving until it hits a wall or boundary, counting the steps taken along the way, and updating the new position. Second, priority queue operations include pushing nodes with their distances and popping nodes in the order of increasing distance. This ensures that paths are processed in the correct order. Finally, the distances array is updated only when a shorter path is found, which helps us avoid redundant computations and ensures that the algorithm remains efficient. To analyze the complexity of this solution, let's consider the dimensions of the maze, n rows and m columns. Each cell is processed at most once, and for each cell, we simulate rolling in up to 4 directions. The rolling process itself can take up to O, max, n, m, time in the worst case. Therefore, the total time complexity is O, n asterisk m asterisk max, n, m. For space complexity, both the priority queue and the distances array have a size proportional to the number of cells in the maze, which is O, n asterisk m. Overall, the algorithm is efficient given the problem's constraints, balancing both time and space considerations effectively. Here, we start by importing the necessary function heappop and heappush from Python's heap module. These will allow us to efficiently manage our priority queue for Dijkstra's algorithm. We then define a class solution and the method shortest distance, which takes in 3 parameters: the maze, the starting position, and the destination. The maze is represented as a 2D grid, where 0 indicates an open space and 1 represents a wall. We calculate the number of rows and columns in the maze and initialize a distances matrix with all values set to infinity. This matrix will store the minimum distance required to reach each cell. We also define the 4 possible movement directions: right, left, down, and up. The roll function is a helper that simulates rolling the ball in a given direction. It keeps moving the ball until it either hits a wall or the boundary of the maze, tracking the number of steps taken. This function returns the new position of the ball and the number of steps moved. A priority queue, represented as a min heap, is initialized with the starting point and a distance of 0. We then set the distance of the starting position to 0 in the distances matrix. Now, we begin processing the heap where we repeatedly extract the cell with the smallest distance. If the current position matches the destination, we return the distance. If the current distance is greater than the recorded distance for this cell, we skip further processing for this node. For each possible direction, we calculate the new position and distance using the roll function. After determining the new position and the number of steps taken, we calculate the potential new distance as the sum of the current distance and the steps moved. If this new distance is smaller than the previously recorded distance for that cell, we update the distances matrix with the new value and push the updated distance along with the new position into the heap. This ensures that we continue exploring the shortest paths first. Once all possible moves have been processed, if we reach a state where the heap is empty and the destination hasn't been reached, we return -1 to indicate that the destination is not reachable. This implementation ensures that we efficiently find the shortest path in the maze using a combination of Dijkstra's algorithm and a priority queue. Here, we start by defining the structure of our solution. First, we import the necessary libraries, including java.util** for data structures like priority queue. The shortest distance method takes the maze grid, a starting point, and a destination point as inputs. We initialize the dimensions of the maze as rows and calls, and then create a 2D array distances to keep track of the minimum distance to each cell. Initially, all values in this array are set to integer.max_value, indicating that these cells are not yet reachable. Next, we define the possible directions of movement in the maze: right, left, down, and up. To prioritize the shortest path, we use a priority queue, where the elements are ordered by their distance from the start. We begin the process by adding the start point to the queue with a distance of 0 and mark its distance in the distances array as 0. The main logic is implemented in a while loop that continues as long as the priority queue is not empty. Inside the loop, we retrieve the cell with the smallest distance from the queue. If this cell is the destination, we return the current distance. We also check if the current distance is greater than the recorded distance for this cell. If it is, we skip further processing for this cell to ensure we always work with the shortest path. Next, for each cell, we explore all possible directions. Using a for each loop, we iterate over the directions array to simulate rolling the ball in each direction. Inside the loop, we initialize nx in New York as the current cell coordinates and a count variable to track how far the ball rolls. Then, we use a while loop to continue rolling the ball in the current direction until it either hits a wall or goes out of bounds. Each time the ball moves, we increment the count and update nx in New York accordingly. After determining the new position and the distance traveled, we calculate the new dist by adding the count to the current distance. If this new distance is less than the recorded distance for the new cell in the distances array, we update the distance for that cell and add it to the priority queue for further exploration. This ensures that we only process cells that might lead to shorter paths. Finally, if we exhaust all possibilities and never reach the destination, we return -1 to indicate that the destination is unreachable. This implementation efficiently uses Dijkstra's algorithm to ensure we find the shortest path in the maze, leveraging the properties of a priority queue for optimal performance. Let's start with the first example. The maze is represented as a grid where 0 indicates an open path and 1 indicates a wall. The starting position is at 0, 4, and the destination is at 4, 4. First, we initialize the problem variables. The maze has 5 rows and 5 columns. A distances array is created to keep track of the shortest distance to each cell, with all values initially set to infinity, except for the start position, 0, 4, which is set to 0. We also define the possible directions for movement: right, left, down, and up. Lastly, we initialize a min heap with the start position and its current distance, represented as 0, 0, 4, where 0 is the distance, and 0, 4 is the position. Now we begin processing the heap. In the first iteration, we pop 0, 0, 4 from the heap, meaning we are at position 0, 4, with a distance of 0. From here, we attempt to roll in all 4 directions. Rolling to the right hits a wall immediately, so the position remains 0, 4, with no change in distance. Rolling to the left, the ball travels to 0, 0, with a distance of 4. Rolling downward, the ball reaches 4, 4, with a distance of 4. Rolling upward hits a wall immediately, leaving the position and distance unchanged. The distances array is updated to reflect the newly calculated distances. Distances 0, 0 equals 4 and distances 4, 4 equals 4. These new positions are added to the heap as 4, 0, 0 and 4, 4, 4. In the second iteration, we pop 4, 0, 0 from the heap, placing us at 0, 0 with a distance of 4. Rolling to the right, the ball reaches 0, 4 with a new distance of 8. Rolling to the left hits a wall immediately, leaving the position and distance unchanged. Rolling downward moves the ball to 4, 0 with a distance of 8. Rolling upward also hits a wall immediately, again leaving the position unchanged. Since the distances 2, 0, 4, and 4, 0 are already smaller in the distances array, no updates are made in this iteration. In the third iteration, we pop 4, 4, 4 from the heap, which places us at 4, 4 with a distance of 4. This is the destination, so we return the result as 4. The shortest distance from the start to the destination in this example is 4. Moving on to a new example, the maze and its dimensions remain the same, but the destination is now located at 3, 2. We follow the same initialization steps as in the first example. The distances array is reset, and the min heap is initialized with the start position. During the heap processing, we apply the same rolling logic as before. After processing multiple nodes, the shortest path to the destination, 3, 2, is determined to have a distance of 9. Hence, the output for this example is 9. Now let's examine one final example where the maze layout is slightly different. The start position is 0, 0, and the destination is 4, 4. As in the previous examples, we begin by initializing the distances array and the min heap. Using the same rolling logic, we process the heap iteratively, updating distances and adding new positions to the heap as we find shorter paths. In this maze configuration, the destination, 4, 4, is reached with a shortest distance of 12. Therefore, the output for this example is 12. This demonstrates how the algorithm effectively computes the shortest path in different maze configurations and destinations. To analyze the time complexity of our solution, we start with the initialization step. Here, we create a 2D list called distances to store the shortest distance to each cell, and this requires m*n time, where m is the number of rows and n is the number of columns in the maze. Next, we consider the heap operations used in Dijkstra's algorithm. Each cell in the maze is added to the heap at most once, and since there are m*n cells, the number of heap push and pop operations is also m*n. Each of these heap operations, whether a push or a pop, takes log m*n time because the heap size is proportional to the number of cells. Finally, we account for the roll function, which processes up to 4 directions for each cell. In the worst case, the ball can roll all the way across a row or column, resulting in max mn time per direction. Thus, the total cost of rolling for each cell is for max mn, which simplifies to max mn. Now, combining all these components, the total time complexity is calculated as follows. The heap operations contribute m*n times log m*n, which simplifies to m*n log m*n. For rolling in all directions, we account for m*n cells, each requiring max mn time, resulting in m*n max mn. Adding these together, the overall time complexity becomes m*n log m*n plus max mn. For space complexity, the heap can hold up to m*n elements, which requires m*n space. The distances matrix also uses m*n space, as it has the same dimensions as the maze. Since the roll function is implemented iteratively, it does not add extra space for recursion. Therefore, the overall space complexity is m*n. When comparing this optimized solution to a naive approach, the difference in efficiency becomes clear. A brute force method would explore all possible paths from the start position, calculating the distance for each. Given the exponential growth in the number of paths, the time complexity of such an approach would be m*n, which is highly inefficient for large mazes. In contrast, our optimized solution leverages Dijkstra's algorithm with a priority queue, ensuring that each cell is processed only once with its shortest distance. This avoids redundant calculations and unnecessary path evaluations. The use of the roll function further enhances efficiency by allowing the ball to move directly to the next stopping point, skipping intermediate cells. This combination of techniques makes the optimized approach far more scalable and practical. Analyzing the best, worst, and average cases provides additional insight into the algorithm's performance. In the best-case scenario, the destination is very close to the start, and the maze has minimal obstacles. Here, the time complexity is dominated by the small number of heap operations, resulting in O log m*n time. On the other hand, the worst case occurs when the destination is located far from the start, requiring traversal of most cells in the maze. In this scenario, the time complexity reaches O m*n log m*n plus max m*n. For the average case, the maze contains a moderate number of obstacles, and only a subset of cells needs to be traversed. However, the time complexity remains bounded by O m*n log m*n plus max m*n. The reason these bounds hold is rooted in the algorithm's design. Each cell is visited at most once with its shortest distance, and the combined logarithmic cost of heap operations and linear cost of rolling align with the derived complexity bounds. This ensures the analysis is both mathematically accurate and reflective of real-world performance. One common mistake to watch out for is misunderstanding the ball's rolling behavior. Unlike traditional shortest path problems, where you move step by step to adjacent cells, here the ball rolls continuously until it hits a wall. This means you need to simulate the ball's movement correctly and cannot simply treat neighboring cells as directly accessible. Another pitfall is revisiting nodes unnecessarily. If you don't keep track of the shortest distance to each cell, you might end up processing the same cell multiple times, leading to inefficiencies. Using a priority queue for Dijkstra's algorithm or a visited set can help avoid this issue. Additionally, handling edge cases is critical. For instance, what happens if the start or destination is surrounded by walls, or if the destination is completely unreachable? Forgetting to account for these scenarios can lead to failures in your solution. Finally, be cautious with priority queue updates. When using Dijkstra's algorithm, ensure that you update the queue only when you find a shorter distance to a node. Failing to do so can result in exploring suboptimal paths and incorrect results. Inefficient direction handling is another potential issue. Some solutions compute stopping points for the ball in all four directions without optimization, which can be computationally expensive. Others fail to account for boundary conditions, leading to out-of-bounds errors. Shifting gears to interview strategies, this problem highlights your ability to adapt classical algorithms like BFS or Dijkstra to meet specific constraints, like the ball's unique rolling behavior. Optimization is key, so emphasize your use of priority queues to minimize redundant calculations. Interviewers often test your ability to handle edge cases, so clearly explain how you would deal with unreachable destinations or complex maze configurations. Lastly, be ready to analyze time complexity. Since you explore every cell in four directions, the complexity is O m*n log m*n, with Dijkstra's algorithm, where m and n are the maze dimensions. Demonstrating your understanding of this complexity can leave a strong impression. This problem is part of a broader family of related challenges. For example, LeetCode 490, the maze, focuses on determining whether any path exists between 2 points, rather than finding the shortest path. LeetCode 499, the maze 3, builds on this by requiring not only the shortest path but also the lexicographically smallest path string when paths are tied. Another related problem is LeetCode 787, cheapest flights within k-stops, which applies shortest path algorithms to a graph of flights instead of a grid. Lastly, LeetCode 1091, shortest path in binary matrix, is a simpler shortest path problem in a grid that focuses on BFS basics. Exploring these related problems can deepen your understanding of shortest path algorithms in different contexts and help you build transferable skills. There are also alternative approaches to solving this problem. Breadth-first search, or BFS, is one option. It's simpler to implement since all paths are treated equally, but it's less efficient than Dijkstra because it doesn't prioritize shorter paths. This can lead to unnecessary explorations, making it slower for larger mazes. Dijkstra's algorithm, on the other hand, leverages a priority queue to prioritize the shortest known path, ensuring greater efficiency. It's a bit more complex to implement, but the trade-off is well worth it for problems where shortest distance is required. Finally, the A** search algorithm introduces a heuristic, like the Manhattan distance to the destination, to prioritize promising paths. While A** can outperform Dijkstra if the heuristic is accurate, it can become overly complex if the heuristic is poorly chosen. Each approach has its strengths and trade-offs, so it's important to choose the one that best fits the problem's constraints and requirements. Great job! Today, we tackled the Maze 2 and explored efficient ways to solve grid-based shortest path problems. Remember, priority queues and BFS are powerful tools for these scenarios. Stay curious and keep practicing. Don't forget to like, subscribe, and share for more insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!